Yeah, look here. I need it. So you're really from? Where? Actually, I live like
Okay. Hello everyone. Welcome to our monthly talk. So today's topic is Introduction to Survival Bias and Bayesian hierarchical modeling. So,
Oh yeah.
okay. So we are TDP, Taiwanese data professionals. You guys probably have know that. And we are held monthly event about data science. So we welcome everybody who is interested in data science, and we're not limited to only Taiwanese. Like people just can just come. And we apologize for the resolution because their projector is out of function, so we have to bring out a little stuff. Yeah, big person. But we're still very thankful because we have like free space here and like comfy space for our monthly event. So please just bear with our poor resolution and listen to we're like talking. And here's a code of conduct. So we're following this code of conduct for like avoiding any harassment or misconduct. So everyone have to behave, okay? And here's today's schedule. It's very blurred, sorry. So we have two speakers. After the talk, we have a Q&A following, and after the two talks, we have another networking time. So feel free to like chat and because this is gone. So yeah. Okay.
Yeah. So is Sam here? Sam, yeah. Okay, cool. So I'm gonna talk about event for non-focus. Yeah. So non-focus summit is going to be on September 22nd through 25th, and the idea. So what happens there? So who has heard of non-focus? Okay, so like, oh yeah, who has heard of pandas? And okay, a lot more, right? So a lot of the open source software are sponsored by this nonprofit foundation called Non-Focus, and they have and since it's not open source projects, they need a lot of contributors, and people who can contribute don't necessarily have to contribute the code. They can also contribute to documentation, making things more clearly. So the idea is at the summit, it's a 4-day things where you as a user can give feedback on how to make the project sustainable. So you should sign up for that. And the idea is they want to engage with people who are involved in open source data science but don't get to contribute for whatever reason. And so if you have some programming experiences and you just want to know more about it, let me know, and I can connect you with Sam, who should be here in a bit. Yeah.
So we have two speakers. Let me introduce the first. The first one will be Hongren. Yeah, over there, and she will be the second speech. And Gary over there. So come on. And let's go.
Hi everybody, I'm Gary. That's very comfortable to say this. You didn't expect that. So today I'm going to talk about, based on my past experience in AMAX, I'm going to talk about survival bias and a practical solution in the commercial world. So I hope everybody can see, because I'm going to show some graph. Just move in if you can't see the graph. So just a quick self-introduction. I graduated from Management Science Engineering. It's a program between Columbia Engineering School in conjunction with Columbia Business School. Graduated 2017. And then before that, I was in Taiwan, so I get a master and a bachelor in Taiwan from Tsinghua University. And my work experience, last year I joined AMAX, and I was doing customer acquisition last year, 2017. And 2018, I started doing customer engagement. So basically what I talk about today is what I was doing last year. And before that, I was working in Taiwan. All right, so I'm going to go into a topic today. I'm first going to tell about a story, right? So the story is about American scientists during the World War II, that they are trying, this scientist has a mission, that he needed to try to improve the armor on their fighter, so their fighter can last longer during the fight, during the battle with Germany, okay? So the scientists think about, okay, to do that, let me look at the sample that we have came back from World War II. Look, he has a specific point of looking at the bullet hole distribution on the fighters, right? He has an idea about if we improve the armor around the region where there's a lot of bullet holes, then we could definitely make the plane last longer. Okay, so after examining a huge amount of sample of fighters that came back, he found out that most of the bullet holes are centered around the wing area, where the two axes is. See, the wing area. So therefore, he had a conclusion, like due to the distribution of the bullet holes are statistically significant centered around the wings, we should strengthen the armor around the wings to make our fighter last longer, all right? So before going to, I'm going to tell about a story, but does anybody feel suspicious about this statement? Okay.
Yeah, other people.
You graduated from statistics, okay. So think about, so the scientist thought that he's looking at a comprehensive sample, but however, he's missing out some samples. The sample that he's missing out are the samples that didn't came back. How about the planes that never came back from World War II? What would their distribution of bullet holes look like, right? For those planes who never came back, there's a possibility that the distribution of the bullet holes is in the cockpit. That's why the fighter got shot off and they cannot come back for analysis. That's a possibility, but we don't know. So that is called survival bias. Survival bias means that you only know the sample that you know, but you cannot gather a sample gather information from a sample you don't know. All right. So for survival bias, it naturally exists in all customer targeting framework. So think about you have 1 million customers in the US, you can only target 1,000 of them. The data that you get is only from those 1,000. You don't know the other, how much is that? The rest of the numbers, right? So that makes your sample bias, even though that you analyze all the sample you have. So naturally exists in all customer targeting framework. The ideal world that I'm talking about is that if you have a universe of 1 million US customers, the ideal world is that you know every one of them. You know their perfect distribution. You know their rewards, and then you're gonna target those with high probability of responding, whatever, right? That is an ideal world. But in the real world, it doesn't work like that. It is feasible to test out all the population, and there's no way they can understand like 80% of the population. So the main topic today I'm going to talk about is the question mark below. So how do we adjust our targeting algorithm and be able to reach an expected optimal outcome? The expected optimal, I'm saying expected because you're never going to reach the ideal world situation. So that's the expected optimal. So how do we reach the expected optimal outcome given that we only have limited information? So that is the question that we have today. All right, so before going to the algorithm, I want to bring up a case so that we could discuss around the case. So today's case, I'm going to talking about advertisement ads. It's easy, like when you go on Facebook, other way around, like for AMAX, right? Today you have a million US customers. You can only show ads to 1,000 of them. So this is the framework that we're talking about, this, the case that we're talking about today. So the first one, I'm going to talk about some scientific definitions so it will be easier to discuss, we'll be on the same page. So first is the reward. So reward in our case is whether the customer clicked your ads. When you show the ads to a specific customer, if I show it to Robin, if Robin clicked or not, it's a 1 and a 0 outcome. So it's a Bernoulli trial in our case. The reward will be so right now, if I targeted like 1,000 customers, right? the regret is between when you're in the ideal world, how many customers will you target, the difference of that situation and the 1,000 you target. Because that is the regret, because you're never going to reach optimal. So the difference is called regret, okay? Then the large number K. So K means the number of customers. So when we have 1 million customers, we target 1,000. K is 1,000. K is the variable that which for every round we're gonna target. And each of the customer has the reward probability theta 1 to theta 10. So if Robert click our ads 1 out of 10 times, then he has a mean reward of 0.1, sorry. And if another person click our ads 9 times out of 10, he has a mean reward of 0.9. So every customer has a reward probability, has a mean reward, basically. And then A means the action you're gonna take. So out of 1 million, you're gonna take 1,000, right? But which 1,000 are you gonna target? That is what we'll call action. And then big R is just accumulated rewards over time. When you do multi-rounds of campaign, like think about you do like 1 campaign per day, you can do 365 per year. The accumulated rewards over time is noted as big R. Accumulated regret is as big L. So the objective function of the algorithm right now today is we want to maximize big R, and same way it's just minimizing big L. So that's clear to everybody. So today, I'm going to talk about 3 algorithms. The first algorithm will be what we call greedy algorithm. So the greedy algorithm works like that. So based on the past 1,000 customers you reach out to, you calculate the reward for them. So basically, if I reach out to Robert 10 times, he clicked it 1 time, so he has a mean reward of 0.1. So we calculate it for everybody and continue to target those customers with high mean rewards. It makes sense, right? We want to target the people that rewards the highest. So there's a serious issue with this approach, okay? So I'm going to talk about an example, which is the robot here. I don't know if you guys can see it. So basically, there's a robot on the left. Just think about that as yourself. Today, you got to decide which restaurant you're going to. You can go to the usual place that you go to like millions of times, that you know that you're going to enjoy the food there. Or you can choose the grand opening restaurant you don't know nothing about. And you probably will get surprised by the food, but you probably get very disappointed. There are possible outcomes, right? So in machine learning world, when you try to go to the same place when you try to exploit go to the distribution that you know about, it's called exploitation. Because you already know about the outcome. You're very confident about the outcome. You just keep exploiting that. That's called exploitation. So the point that is called exploitation. On the other hand, if you go to a new restaurant that you don't know nothing about, you're very uncertain about the outcome. That is called exploration. Okay? So greedy algorithm is purely doing exploitation, but not exploration. It's just exploiting what you already know in this algorithm. Keep targeting those customers with high rewards. In general, you perform really bad because think about this, the scientists, right? You only are limited to the sample you know. You're never going to know more about it. So that performs really bad. An improvement on the greedy algorithm is what we call epsilon greedy. So epsilon greedy works like this. For every round of actions, for every round where we target customers, with epsilon probability, you're going to reach out to you're going to take a random action. You're going to take a random action to explore what you don't know, open up to the population, right? And with 1 minus epsilon probability, you're going to pick the best action that we have learned so far. So basically, epsilon greedy is just doing epsilon probability for exploration, and 1 minus epsilon for exploitation. So basically, every round, you learn a little bit more about the unknown population. So the epsilon should be small, and this generally works a lot better than greedy algorithm. Okay? So what about the problem? What's the problem with this approach? So I don't know if, let me know if you can see this, but there are problems with epsilon greedy algorithm, okay? So the advantages of epsilon greedy is that you're doing random explorations so that you have an opportunity to try options that you don't know much about. You're learning new stuff from the population, right? But what the disadvantage of that is that due to the randomness, it is possible that we're going to end up exploring a bad action even though we have confirmed in the past. That is called bad luck. So here is just a part of the PDF of 3 actions, right? So you compare action 1, the blue one, and the action 2, the green one. Both of these PDF are really tiny because we try them out a lot of times, though the power density function get tinier and tinier. But then you confirm that action 2 is way worse than action 1. But when you use epsilon greedy algorithm, there's still a random chance you're going to pick up action 2, even though that you know that's real bad. So that is a potential regret you're going to meet if you use epsilon greedy. Okay. So what do we really want to do? A better algorithm will be we want to, for every round of actions, we do want to explore more stuff. We want to explore the unknown population, but not randomly, but with intelligence. The intelligent means that we want to have a preference to uncertainty. So think about a customer you reach out to them 1,000 times and a customer you reach out to them 2 times. You want to give a chance to keep trying out the 2-time guy because probably they could give you a very high reward. So the algorithm that we want to explore randomly. We don't want to explore randomly, but we want to explore with intelligence. So how do we do that in the number-wise algorithm, right? So yeah, so the thing that I want to share today is basically, it's called Thompson sampling algorithm. So everybody heard about Thompson sampling? Nice, okay, thank you. Okay, so Thompson sampling works like this, okay? Before I go into the characteristic of how we use this algorithm, we're going to talk about the mathematical equation. I'll just quickly go over it, okay? So for every round of action, so for epsilon greedy, we sample the theta k. Can you see it? Okay, so for every round of action, for epsilon greedy, I'm gonna calculate theta k based on past experience result, right? Just like what I said, if Robin clicked my ads 1 out of 10 times, he has a mean rewards of a 0.1. So epsilon greedy is doing that. Thompson sampling on the other hand, we sample a random number from the beta distribution. Beta distribution, there is the ugly stuff below there, but there are 3 parameters that go into it. Alpha mean the number of prior success, beta mean the number of prior failure, and theta just being your reward probability. So instead of only calculating theta, the alpha and beta is how many times prior to this time action I have reached out to Robin. So if I reach out to you 10 times, you responded 5 times, but you didn't click it 5 times, your alpha and beta will be both 5. So every round of action, we pick a random number, we sample a random variable from this distribution, and we target based on that. And after we try out this customer, we then update your alpha and beta. So for example, if I pick Robin using this distribution, he then clicked the ad, I'll update the alpha by alpha plus 1, and beta remains the same. So what is the characteristic of using this instead of epsilon greedy, right? Well, this is just a pseudocode for doing between Bernoulli greedy and Bernoulli Thompson sampling. You can see the only difference is in the region when Bernoulli greedy is updating the theta k hat over using that equation, and for Bernoulli Thompson sampling, we're sampling it from the beta distribution. So what is the characteristic of that? Okay, so so you're comparing like action 1 and action 2 and action 3. So action 3 is so large because the confidence interval is very wide. We don't know much about it. For action 3, we only tried them total of 5 times, and action 1 and action 2, we tried them both 1,000 times. So in this case, you don't want to take action 2, right? Because it has a mean reward. You're confident about this mean reward falling within this region. However, you want to take action 3 because it may probably you'll probably have higher mean reward when you further test it out. So when we sample a random number from the distribution, right? When you sample one from action 3, it's possibly that you're going to sample a random number here, right? But it's also a possibility you're going to sample it here. So when you sample a random number from action 3 distribution, because it's the highest, and comparing it to action 1 and action 2, you're going to pick action 3. So what Thompson sampling does is that because you're picking a random variable that has distribution very wide, you're probably going to pick out the action 3 because it is very uncertain. Okay? So therefore, it gives action 3 a probability to be picked. This is the first characteristic. The second characteristic is after you remember the alpha and beta we talked about. After you pick certain action a lot of times, the confidence interval getting lower and lower. The confidence interval getting tinier, right? So in this case, after further rounds, you're not going to pick action 2. Because when you sample random variable from action 2, you're going to fall within these region. When you sample random variable by action 1, you're going to sample within these region. It's highly unlikely you're going to pick action 2. So this solves the randomness of epsilon greedy when you have multi-round of actions. So the two main two main characteristics of Thompson sampling algorithm is because of this. Either you can eliminate the randomness, and you can give actions with higher uncertainty a chance to be picked. Okay. So here is just comparing epsilon greedy, which is the blue one, and Thompson sampling, which is the green one, which we call it cumulative regret. Another good characteristic about Thompson sampling is that after you try out a lot of times, because of the confidence interval getting tinier and tinier, you tend to convert to only those actions with high rewards. So you see that the cumulative regret converge over time. On the other hand, if you use epsilon greedy, because of the randomness, you keep picking random action with probability epsilon, the cumulative will still keep accumulating. So it goes from here to here. Compared to Thompson sampling, it converges. All right? So one point a caveat that I want to stress here is, after a certain round of sample, you know the Thompson sample is converging. However, in the first couple rounds, you'll see that the regret for Thompson sampling is way higher, because when we have a lot of action that we don't know, Thompson sampling tends to keep picking up random actions or picking up uncertain actions, so we can know more about the reward. So in the very first phase, you'll see that Thompson sampling has a higher regret. However, it converges over time, and comparing to epsilon greedy. So how many times do you have?
About 10.
Another 10 minutes?
Yeah.
I thought it was going to be like 30 seconds, I'm going to end it. Okay, so, cool, okay. So I'm pretty sure that you can't see anything of this, so I'll just go through this quickly. Basically, this is the same test, but this is a test from Stanford University. So what he's trying to do is to solve a shortest path problem. So anybody know about shortest path problem? I know Janice does. Okay, already does. Okay. So shortest path problem is you want to get from node 1 to node 12 with the shortest path. You don't know anything about the distance between those nodes. There's a lot of algorithms out there you can use to find out the shortest path from 1 to 12. However, this question is a little bit more advanced. Instead of deterministic number between distance, they sample this from a Gaussian distribution. So therefore, you're not quite sure about. You need to try multiple design to make sure that to be more confident about the reward. So, like plain English means that from New York to Boston, New York to California, you know it's close to 4,000 kilometers. But right now, instead of 4,000 kilometers, it is sampling from a Gaussian distribution with a mean reward of 4,000 kilometers. So you need to try out multiple times to make sure that you reach the shortest path. Okay? So it's the same thing as the shorting ads to customer, right? Because when a customer didn't respond, you say, hey, you don't respond, but because we only reach out to you very low number of times, I need to try you out. I need to test you more to gain a more confidence in you, right? So basically, it's the same dispute of exploration and exploitation. So here is just two results from between using greedy, epsilon greedy, and Thompson sampling. So this reward, if you see, this is called per pure regret. Given that using this algorithm by design, the path that you choose, how is it comparing to the optimal distance, right? So, okay. So you see that after a certain amount of time, only Thompson sampling converges, while both of them, all of them converges. However, you see that greedy has a really bad outcome, because what greedy does is that from 1 to 2 to 6, right? After you choose a distance that is the lowest, you continue to choose that one because you believe that is the lowest. However, that could just be, because this is a random variable, you also need to try other of these edges because there's probably be that their mean is lower than this. Greedy algorithm doesn't try this. So it means the optimal outcome is the worst. Okay? You do epsilon greedy, right? You do epsilon greedy. After a certain amount of time, it is way better than greedy, but however, after amount of time, because of the randomness in the algorithm, you cannot reach the optimal outcome. So only Thompson sampling is closest to the optimal outcome after a lot of rounds of tests. Okay? So the other graph is the same thing, but this is just the total distribution for each round, for each action, the total distance over your optimal distance. So basically, you want to be closer to 1 to get to the optimal outcome. You see the same trend here where greedy has a way worse performance, epsilon greedy being in the middle, and Thompson sampling being the best. Okay, so that's what actually. Wait, okay. So what I want to talk about Thompson sampling is this, given that I have a little bit more time. So Thompson sampling is widely used in reinforcement learning. So everybody heard about reinforcement learning, multi-arm banded. Thompson sampling is specifically used for Bernoulli trial, when you have a 1 and 0 outcome. Then when you have other outcome, for example, like without 1 and 0, there's also a lot other algorithms such as upper confidence bound and some sort of other thing. So basically, this algorithm is widely used in reinforcement learning. So just to summarize what we talked about today, right? So when you want to explore at random, you can use epsilon greedy. But the disadvantage of that is that after a long run of time, you'll never be able to reach the optimal outcome because the randomness in your algorithm. If you want to explore what's intelligent, then Thompson sampling is a methodology that I can use because we're giving a bigger probability for action to be picked if we're uncertain about the action, because that gives us the most information gain. Okay. So the last point I want to talk about is what is the difference between being an optimal solution and a feasible solution, right? So talking about a caveat I talk about here. You see that in the first couple rounds, like Thompson sampling is performing really bad, given the regret is so high, right? Because in the first couple rounds, it tends to explore more actions that you're uncertain about. So think about you going to your boss and saying that, hey, boss, I want to use Thompson sampling as a methodology, but in the first couple seasons, we'll probably perform really bad. But we'll reach the optimal outcome in the long run. So think about whether this is feasible in a business world. So in AMAX, right, because of the round of action is so important here, we started to use this for advertising. However, for traditional DM targeting, DM means that we're sending mail to your home. For DM targeting, for phone targeting, we're still using epsilon greedy. Because in the short run, you think about we only do, like, if we do campaign once per month, we only do 12 per month, right? Or 12 per year. So think about how many times do we need to reach the optimal outcome. This isn't feasible. We think about the characteristic of our campaign. However, if you're doing ads, when you're doing ads, you normally can show ads probably, I don't know, you can show probably, I don't know, like 1 per minute probably? One per minute or 1 per 10 minutes. So therefore, because of the multiple rounds of actions, and because there's showing ads are basically no cost, it would be more feasible to use Thompson sampling on showing ads instead of all of the targeting. So think about the final topic I talk about customer targeting. Depends on the characteristic of your targeting. Still, epsilon greedy is still a pretty good algorithm. Even though it didn't reach optimal outcome, still it performs really well compared to greedy. Okay, so in the real world, there's always this fight between what is optimal and what is feasible. So when you want to use in the commercial world, try to think about what is more applicable to your case. That's all.
Can I ask a question about that?
Yeah.
Just recap. Is it possible, like when you're trying to solve the problem that you have too less observations in your campaigns, can you adjust your priors that to approach your final result that you already know your like click-through rate is low, so you just adjust your prior closer to a final result, and so that you can update and converge faster?
Well, that can't be caught me off guard. Sorry, can you say it again?
Sorry, I mean, the problem here that you can it's a better solution for greedy algorithm in the say email campaign is that you don't have that much observation to reach the coverage for the Thompson sampling solution, right?
Okay, but given the characteristic of email, we have a lot more actions there comparing to direct mail and phone call, right? Because we have more roundabout actions there.
Yeah.
So I would just say that email is a better channel you want to try out Thompson sampling compared to DM and for phone channel. Yeah, that's my point. Sorry.
Alright. What kind of options do you have to adjust the parameters for your Thompson sampling to
yeah.
change
So
the shape of that?
direct. Okay. So yeah, good point. So basically, if you change the two most important parameter is alpha and beta, which is your prior success and prior failure. And after you updated your alpha and beta every each round of actions, your distribution kind of changes, right? The shape of the distribution changes. So you see, this, so action 1 is beta distribution with alpha, beta equals to 601 and 401. And action 2 is a distribution of alpha, beta, 401 and 601. So basically, this is around like 6%. The mean reward for action 1 is around 0.6, this being 0.4. So because they updated, when you update the alpha and beta, the distribution, the shape changes, right? Then you sample from the distribution for a random number. And therefore, it's highly unlikely that action 2 is going to, the random variable that you pick from action 2 is highly unlikely to be higher than action 1 because of the shape, right? So the most important parameter you update each round is for alpha and beta. So we update that for every customer if we reach out to them. And therefore the shape changes and we choose it from that.
So, sorry, you get it.
I'm just curious if like this is possible. So is it possible where you start out with, so you do like a combination of both. So you start out with epsilon greedy and then you calculate where the two lines intersect, and then once it hit that threshold, you would switch to constant sampling. So you would optimize on both sides.
Okay.
You know what I'm saying?
Yeah, but I understand, but I don't think there's a scientific way of telling when will these 2 points meet. So basically, this is from our test results. You only know this after you try both them out. There's no deterministic way because of the randomness inside. There's no deterministic way of figuring this point beforehand.
Okay, cool.
But let's say this, if you start out with the greedy, epsilon greedy, and it goes up, then the green line, let's say, and then you start to try constant sampling again. Will it go down or will it be just flat?
So I'm pretty sure, like, if you're saying that if we try epsilon greedy for a long time, then we switch to constant sampling. Is what you're saying?
No. I mean, if it's keep going up, and then let's say you cross this, yeah, and then you start trying constant sampling. Does it go down or does it keep flat?
Okay, so this is cumulative regret, right? I believe that after after you use time sampling, after you use time sampling, at certain point it's going to converge anyway. The regret keep accumulating is because of the randomness. We're taking that randomness out by adjusting the shape of distribution.
So when you get a new customer, that your prior will set up the as you said, the prior is characteristic by alpha and beta. So you always start with like alpha, beta,
Good point.
0, or you have implement more like prior knowledge into prior distributions.
Yeah, so very good point. So think about if we first get a customers, right? If we get a customer we don't know nothing about, a very simple type of sampling, you start with alpha and beta all equals to 1. When you put 1 into this algorithm, it basically becomes a uniform random variable. Uniform being or mean reward being 0.5. So we have a biased understanding or assumption for you. If we first reach out to you, we have an assumption that you have mean reward 0.5, whether you respond or not respond. So we start with that, and then we update it after. Still, there are all other algorithms that, because of this characteristic of the customers, some research are starting from a different approach, starting with different alpha and beta to make sure that it fits the pattern. But most of the most traditional quantum sampling will start out with alpha and beta all equals 1.
So you don't get advantage if you set that, because you set the high numbers of the, higher probabilities to send to the new customer. Something like that.
There's ways to adjust it, but it really depends on the use case. I can't say that which one is better, but there are use cases like more related to so I'm thinking about a paper, but I forgot about it. So basically, because of your characteristic, some quantum samples starts from other than 1 and 1. Okay, because they believe that your prior distribution, like when we reach out to new customers, your mean reward is not 0.5. Then there's no point that I started to view your mean reward as a uniform random variable.
Just a quick question. So have you tried out your sampling algorithm? Because now we want to talk about constant, and there are so many. Have you tried in your company, for example?
Yeah. So okay, in our company, so basically, when I talk about Bernoulli trial, the entire framework we're talking about is Bernoulli trial, whether the customer has a 1 and 0 outcome. So using that type of sampling is the best method right now. For other kind of framework, when the outcome is not 1 and 0, there are other type of algorithm that I don't have experience in. So right now, because of what I say about this is highly feasible to only ads. We don't use this in any other channel. So because of the characteristic of ads channel, it's either 1 and 0. You click it or not click it, right? So we use auto sampling here.
Okay, we only take one more. Let's think.
All right, so this I want to show my meme that I downloaded. So.
Yeah.
Yeah, that's my meme. Yeah. Okay, cool.
Okay.
So here's the meme that.
Okay, shall we start? So, hi everybody, my name is Yuan Huang, and so I am a machine learning engineer working at a personal styling company, Bayesian, since this January. And before that, I came from a computational physics background, where I developed Monte Carlo algorithms to understand something like quantum materials. And then, since this year, I started to transition into the field of data science and start to work at hierarchical and build machine learning algorithms to help our business in the fashion industry. So first, I would like to talk a little bit about hierarchical, which is an online personal styling company that is dedicated to serve women with plus size and to help her find the best clothes that fit her and make her feel awesome every day. And so we are a box subscription service. So we send out a box of 5 different fashion products to our customer every month, and they can try them out at home and like pick whatever they like and return whatever they doesn't like about the box. So that's our business, and today I'm going to talk about how in my day-to-day job, I use Bayesian hierarchical models to help us to understand our business and to understand better about our customers and products. And today I'll first give a brief introduction about the general idea of probabilistic modeling and Bayesian analysis. And also I will use a simple example to show how to build a simple Bayesian hierarchical model and try to use it to understand the price effect about our customers' purchase behaviors. So first, very broad view about probabilistic modeling. As Gary also mentioned that our daily real-life data always come with noise, with randomness and uncertainty. And instead of just build a deterministic model that only learns some point estimate about the model parameters from data, in probabilistic modeling point of view, we actually want to use some probability theory to capture the random process that generate our data and to learn about the uncertainty in a more rigorous way. And to give a kind of a comparison between the deterministic model and the probabilistic model is that, for example, we want to fit a simple linear regression with some input and output. So for a conventional like machine learning model point of view, we want to learn the point estimate that satisfy the maximum of the likelihood function. Try to find the point estimate for the model parameters that can give us the maximum likelihood given the data that we have seen. But in the Bayesian analysis point of view, we actually want to learn more about the model parameters. We actually want to learn the whole probability distribution of the model parameters. And given the data we have seen and also given some prior knowledge that we have before we have seen any data. And this is the essence of Bayesian analysis. So Bayesian analysis is normally more information efficient because we can generate more information about the model parameters. We do not only have a point value, but we also have the whole possible probability distribution and all the uncertainty associated with it. But it is also more computationally intensive to train the model. So now I will talk about the 3 major components in order to perform Bayesian analysis. First, of course, is we need to have some data, some input and some output. And then the second very important thing is we need a generative model. So a generative model it describes how our data are generated. It's usually in the form of a probability distribution as to describe the random process that actually generates the data we have seen. And so all the generative models will come with some model parameters. And if we actually know the ground truth value for those model parameters, then we can define the probability distribution and we can generate some random data from this generative model. But in reality, what we have is not the model parameters. What we have is actually the data, the very noisy data that you have seen every day. And what we want to do is, given the data we have on hand, we want to learn something about the model parameters and make some inference. And that is what we call Bayesian analysis or Bayesian inference. So in order to do that, we not only need to have the data and the generative model, but another very important part is we need to have some prior knowledge about the model parameters before we have seen any data. So this is our initial guess about how those parameters would be distributed. And so this is usually characterized by some hyperparameters for those distributions. So it also, because we also do not know exactly how those model parameters will be, especially when we don't have any data, so our initial idea would be very broad. So it can be a very flat distribution. And it's also characterized by some hyperparameters. And if we have all those 3 different components, the data, the generative model, and some prior knowledge, then we can start to do Bayesian analysis. So we can apply Bayesian rules and try to calculate the posterior distribution for the model parameter theta. And so in the Bayesian analysis, we will have a prior distribution, which is described by the hyperparameters. And then we will have a likelihood function, which is if we know the ground truth model parameter theta, then how likely we are going to see the data that we have seen right now. And the posterior distribution is actually proportional to the multiplication of the likelihood function and the prior distribution. Okay. Now I want to talk about a very simple example, which is kind of like what I do idea, is that we want to understand the price of our items and how that would affect our customers' purchase. Because idea, we are sending out boxes to our customers every day, and it's very important for us to learn how likely they are going to keep those items. Therefore, we want to just train a very simple model with just the price of the item as the feature, and whether the customer will purchase or not will be our output. So this is also like a Bernoulli trial, so either they keep it or they return it. And a very simple idea would just be to train a logistic regression function for that, right? So in the Bayesian analysis way, it's actually quite similar to that. So first, we want to define the probability for the customers to keep that item, and we want to define it. I'm sorry, probably you cannot see it very clearly, but we want to define the probability as a sigmoid function of a linear curve, so which use this price as a predictor. So we will have a slope term and an intercept. So this is basically just a very simple logistic function. Yeah.
Make it clear.
Yeah, is that better? I really apologize about this. And then we have this probability model. And then at each observation, we just use this to generate a Bernoulli trail associated with this probability, and we will have our data like ones or zeros, whether they keep the item or not. And for this, we also, in order to perform the Bayesian analysis, we also need some prior knowledge about the model parameters, which here are the slope for the price and also the intercept. So if we assume that we do not know much about the model parameter, then we can just find like quite flat normal distribution for all these parameters. But if we also have some like historical understanding about the slope and the intercept, then we can have a more informative prior functions. But here I will just use a rather flat normal distribution. And so in my work, what I'm using is a package called PyMC3, and it is a quite straightforward package that does Monte Carlo sampling for the Bayesian analysis, and you can define like Bayesian models and like multi-level models in a very straightforward and intuitive way. So here are the code with PyMC3. You can see that it's very kind of intuitive. So you first define the prior distributions, which are those two normal distributions, and then you define the sigmoid function, which is the inverse logit function here, and then you pass it into a Bernoulli distribution to generate the data, and you compare it with the actual data that you actually observed, and then this is the whole model definition for this very simple logistic model. But actually, there is one issue with this simple model, because as I said, we are sending like boxes to our customers, and each box contains 5 different garments. So they are all belong to different categories. So we are sending like tops, bottoms, and dresses, and sometimes like handbags or belts or different types of fashion products. And we know that our customer actually have different behaviors about different types of clothes. And also like accessories is very different. So if we just train a simple model as this and try to just learn one slope and one intercept, that will completely ignore the differences between our products. And that will like be a really oversimplification of the reality. And so what are the solutions if we want to learn more about how the different products behaves? So one way is, how about we just train like a separate model for each type of garment? Then we will, for example, if we have 5 different categories, then we will have 5 different models, right? So we can learn 5 different slopes and 5 different intercepts, and that can solve our problem. But with this solution, actually, we ignore the similarities between our products completely. So we treat all the different types of products totally independently. And that also like reduces the size of our data. So it's also not very satisfying. And so those are like 2 very extreme views about how are we going to build this kind of model. And can we find like a middle ground that sits in between, like completely ignoring the difference or completely ignoring the similarity? So actually, Bayesian hierarchical model is kind of behaving like a middle ground for these 2 extreme cases. So for hierarchical models, we still assume for each group of products, we will have different intercepts and different slopes. So we will still have 5 different groups of model parameters. But we are not treating them as totally independently. We are assuming that those 5 different model parameters, they are actually generated from the same distribution. And we kind of give some assumption about this distribution. For example, we can assume they are all generated from the same normal distribution with a global mean and a global standard deviation. And this is actually, in our reality, all kinds of data have some like embedded hierarchy structures. For example, here I use an example of different products. But for example, we can also think about our customers. They can also be grouped into different types of customers. And for example, we can group them by their age, by their location, or by their other features. And so the hierarchy in data is everywhere. And the hierarchical model, especially in the Bayesian type of analysis, is very powerful as it kind of not completely ignore the difference, but also it takes care about the similarities between the different groups of data and kind of build the hierarchy inside the model. So you can learn their differences, but you can also learn their similarities behind it. And so for these group level distributions, we have also some parameters, hyperparameters associated with the overall, how are we going to generate the different group parameters. So these parameters will be called hyperparameters as well. And okay, so this is basically the idea of Bayesian hierarchical model. And now let's try to upgrade our previous simple model to this hierarchical version. And now we still have the feature which is the price of our items. And now we have another feature which is the group index for each of our items. For example, for each box unit we're sending out, we will know that this unit belongs to a top and that unit belongs to a bottom and that one is a dress. And then the outcome is still whether the customer purchased this item or not. And now let's see the definition for our model. It's slightly more complicated than before, but you can see the actual data generation model is still very similar. So it's still a sigmoid function of a linear curve. And now for each group of products, you have different model parameters for each group. And it's still like use this probability to generate a Bernoulli trail for our observations. And each group parameters, beta g and the bg, which is the intercept and the slope, they are generated from a global normal distribution and with some hyperparameters. And also we will need some hyperprior knowledge about our hyperparameters. So for this, we will still use some non-informative, like flat normal distribution to characterize that if we don't know much about the parameters beforehand. Now we can also define this in the PyMC code. So as you can see, it's like very straightforward, like one line-to-line like correspondence. So you first define your hyperpriors for the group parameter distribution, and then you will define the prior, how the different slope and intercept will be generated from this global normal distribution. And then with this slope and intercept, you can pass them into the sigmoid function and get your probability, and then you generate the data with a Bernoulli distribution. So it's all very straightforward. And with this model defined, now how are we going to learn the model with our data? So in PyMC3, this is actually just one line. So you just write pm.sample, and it will automatically assign a sampler for you, and then it will just run, it will pass the data into the model and try to help you to learn the posterior distribution for all the different model parameters that we specified. So basically, in all these codes, all the different, so for example, this mu slope, sigma slope, and all the different model parameters will be learned. And so, okay, and for in PyMC3, it actually supports two major different types of samplers. The one is Markov chain Monte Carlo sampling, and it has some state-of-art sampler such as NUTS and Hamiltonian Monte Carlo, which actually is quite efficient compared to the more conventional metropolis sampling. And they also, but one problem with Monte Carlo sampling is that, so usually it's very computationally expensive. If you want to run with a very large scale data, then the Monte Carlo can take forever. But the beauty of it is if you run it long enough and you make sure that your Monte Carlo sampling convergence, then it will give you unbiased results. So it will not have any systematic error in it, and all you get is from the statistical randomness that with your Monte Carlo sampling, and the statistical errors actually drops with the number of samples you take. So, but as I said, it's very computationally expensive, and you really don't want to apply it with large data, because I tried and it takes really long time. And another option is something called a variational inference. So this is an approximation approach, actually. It assumes your posterior distribution of your model parameter have certain, it belongs to certain type of functions, certain type of, actually it assumes some Gaussian distribution for your posterior, basically. And it tries to fit your data to that kind of, that family of distribution and try to find the best fit for you. But as I said, it's an approximation, so sometimes it can give you some good estimate of probably for the mean, and but it cannot give you a very good estimate about the distribution or the standard deviation associated with your parameters. But it is much faster than Monte Carlo, so this kind of trade-off. So you have to choose. If you have small scale of data, you can try with Monte Carlo. But if you have really large number of data, so probably only feasible way to do some Bayesian analysis is to use the variational inference. And then after we have trained the model, then what can we learn from the output from PyMC3? So here we can try to plot the posterior distribution for all the parameters that we specified in the model. For example, here, the first one is the mean of the global, the global mean for all our 5 different group slopes. And this is the global mean for the intercepts. And we can also learn all the different slope, the price, slope to the price, and the intercept, like for different type of products. So you can get the whole posterior distribution. And also you can get some statistics about, for example, you can get the mean value for all the parameters and standard deviation and the confidence interval and all that, because you already have the full distribution, so you can get as many statistics you want. And this is basically how the Bayesian hierarchical models will work. And but there is some, and there are also some way to check whether the results you get is reasonable or not. Because as I said, Monte Carlo is really painful to train and it's very slow. And for variational inference, it is an approximation. So you always want to check those assumptions is valid or not in your data. So there are some diagnostics. For example, you can run some posterior predictive check, which is you already learned all your model parameters. Then you can try to use this model you learned to generate some random data and compare it with the actual data you observed. And this is called a predictive check. So you can see how would the distribution of your generated data compare to the actual data and try to see if the distribution actually matches with each other. And specifically for Monte Carlo, there are also some sanity checks. For example, you can look at the autocorrelation within the samples you are generating from the Monte Carlo chain, or you can try to do some convergence test, or try to see the effective number for the samples and try to see whether there is some issues with your Markov chain samplings. And for the variational inference, you can also do some check goodness of fit and try to see if the approximate function actually is consistent with what you see in the data, and try to see if you have a good statistics for example, the KL divergence and some other metrics that is quite important to check whether the result actually converges or not. And I think that's mostly what I want to talk about Bayesian hierarchical models. And here I put some references, some books and tutorials and YouTube lectures that I really enjoyed, and I really learned a lot from them because I didn't come from a statistics background, so I kind of all picked up from all these great materials. And
so now we're
questions.
So when you set a hyperparameter for your master distribution for your parameters, I want to know because sometimes you assume a distribution, and then do you need to scale it? Because if the underlying is not Gaussian at all, we know it's the limit theorem can approximate in some way. But if you don't scale it, never converge to it theoretically. But in practically, do you see convergence? You just give the random Gaussian and then still converge if you have enough data.
So I guess the question is, if you know that your posterior is not a Gaussian distribution, but you start with a, I mean, I'm trying to understand your question.
So for you,
Yeah.
you assume this is a distribution for your hyperparameters.
Yeah, I assume that you mean like the prior distribution?
Yeah.
Right.
You want to do Bayesian update learn this
Mm-hmm.
to estimate these parameters.
Right.
Yeah, and so I guess here, I can go down. No, like the hierarchical model.
This one?
No, hierarchical.
Oh, hierarchical. Exactly. Okay. So I guess your question is whether this distribution is valid or not. Hyperpriors.
Yeah.
Oh, I see. I see what you're saying.
Yes.
Yeah. So I think, yeah. So the prior knowledge we have for those, whether it's a hyperparameter or the parameters, I don't think that it actually matters a lot when you have more and more data. Like, yeah. So your posterior will get narrower and narrower when you have more and more data and more information. So the prior would be just like initial guess when you really do not have any experience with the data. So even if you start with a normal distribution, if your data tells you otherwise, then you will still learn a non-Gaussian distribution for your posterior.
Yeah, so practically how many you need. Practically you're just want to get a sense for critical application.
Right.
Yeah.
I guess, yeah, because in reality what I see is that because our data is always quite noisy, and as I said, we are also introducing a lot of bias when we apply some inference, like, yeah, a lot of approximations here. So it's not like it's not a very ideal data set to test whether our posterior we learned from the PyMC model actually matches with the data, because we do not know the ground truth. But I assume that we can run some experiments. For example, if we know already like how the data is generated, and try to simulate some data and try to train it again. So yeah, I mean right now actually I'm working on something very similar to what you described here. But I haven't come to a conclusion about that. But yeah, it's a very interesting topic. Yeah, thank you for the question.
Related question. So
right.
In reality, do you need to just check like different priors doesn't affect the result? I mean, if your result is too sensitive to prior, then your data tells you nothing.
Right, exactly.
So,
normally,
like in practice, do you really need to test different priors, like low prior, flat prior, Gaussian, and then make sure that data, the result is really insufficient to prior?
Mm-hmm. Yeah, that's a really good question. Actually, so in reality, what I see more is, so normally what I see is the result is not sensitive to the prior. For example, if I change the standard deviation for the prior, or I completely change it from a normal to something like a uniform with a very large range, then the results will not change much. What matters more is the model definition, like what kind of features you want to add into the model and how you want to, there are some other things called reparameterization. Like you can define the distribution in a lot of different ways. Like here, for example, you say that the prior starts with this normal distribution with a mean, like a non-zero mean. But you can also say it starts with a zero mean, but plus some constant term. And if you parameterize it differently, then sometimes you will get different results. So actually it's more sensitive with more subtle things. Yeah, I agree kind of, like Bayesian analysis is, sometimes it's very tricky to learn, especially when you have very noisy and large scale data. Yeah.
Actually, I have a question. So, what about you tell us about the box? So, do people return it, or do people buy it, or like they just being lazy, they don't want to like return? So, tell me more about it.
Cool. Yeah. So actually, all this kind of scenario happens. Like normally when we send out boxes, so we have some customers who are performing very well. They will just make a full box purchases. And sometimes they will try it out, and we ask them to return the items they don't want in 5 days. and we can get some returns, like maybe they will return 3 or 2 different pieces back. And sometimes they just, as you said, they are lazy and they forgot to return anything. So at the end, they will just purchase the whole box. But that actually happens like relatively very rarely in our business. So yeah, a lot of our customers are like performing very well, and they really love our items and products, and they kind of post their like pictures with the clothes on. They're really happy to try them on. Even sometimes they do not buy it, they still leave notes to say that I actually really like this clothes, but I don't have the budget this month. So can you please send them out to me like next month? So yeah, it's really interesting to see like how different customers like react to our boxes. Yeah.
I have like a box related question
Sure.
as well.
Yeah.
So like based on like what the customer has like returned, do you guys like customize or like adjust what you send the next one to a specific customer?
Yes, exactly. So we have, so in our business, we have like two-stage kind of recommendation type. So first we have algorithm that is a recommender system that kind of show, based on your purchase history and like your box history, it kind of generates a recommendation list.
Yeah.
And then we have our stylists who work from this list and try to pick what to put in the next box. So so every stylist will go through each customer's history and try to see what types of clothes they like or what they don't like, and what kind of clothes they already have. And then based on all these histories, they will pick from the list that's generated from the recommender. So we first have a recommender, and then we have a personal stylist who can actually do the selection for you. And they will like even write some styling notes to tell you this one will go very well with the other one. You can put them as an outfit and what kind of occasions that you can wear this to.
So you basically have like an algorithm that makes prediction, but you also have like the human element to like make it more.
Exactly. Yeah.
I have two questions. First, you mentioned the P1 is pretty slow, but to my knowledge, I remember last one is backend Seattle, right? It's not.
Yeah.
No?
It is back down by in Seattle. Yeah, exactly.
So it's kind of, is it not possible to speed up like this network car or some kind of technology to make it much faster? That's my first question.
Yeah.
And another question that was we already filled all the batches. But I have another question that is the problem of turns out is like the information problem like the main system, right?
I mean, so here the example I give is like an oversimplification of the actual problem, but my goal is trying to predict whether they will purchase or not. Yeah, it's kind of like a recommend. Yeah.
I'm wondering because there's another kind of popular model like Bayesian machine. I just want to compare these two models, method which one is the pro and cons on what you choose the publicity model.
Can you say the model you
There's another popular modeling method called factorization machine.
I see, like matrix factorization.
Yeah.
Is the matrix factorization like?
There's another similar term as mentioned as factorization, or you can say factorization machine is a classifier.
I see.
Yeah. So what you want to do, if you possibly comment on this method over the publicity modeling method?
Yeah. So for the first question is that right now PyMC3 is based on Ciano, and is there any way to, for example, use any like graphical card and like make it faster to run? Is that the question? So actually, so my knowledge is that PyMC. So right now we are using PyMC3, but PyMC4 is also in development. And for PyMC4, they are actually going to use TensorFlow as a backend. And I believe that will make it faster because you can do parallelization and you can run it on GPUs. So I believe with that PyMC4 coming out, it can make the Bayesian analysis more efficient, hopefully. Yeah. And I think he also have a second question, which is how does this probabilistic model compare to some recommending algorithms such as a factorization machine. So to be honest, I don't have a lot of experience in factorization machine, and actually in my project, I'm now trying to build a recommender. I'm actually more interested in learning how the price for our products actually affect the overall conversion rate instead of making individual predictions. But in our business, our company actually uses the matrix factorization, and I think it uses something like a light FM to do the recommenders. So yeah, so that's actually what we're using. But so for this project, I'm kind of just learning some overall, like make some inference based on the data we have.
Yeah. One more question.
Yeah, I think you have a question.
Just a follow-up question. So,
Yeah.
you talk about parallelization, but can you do parallelization in MCMC? Because you are doing learning walk.
Yeah.
If you don't know the previous step, you cannot do the next one.
Yeah.
Yeah.
So
like
in
different methods together and join them.
yeah, in Markov sampling, Markov chain Monte Carlo sampling, you can build like totally like parallel Markov chains and run them parallelly. And but the thing is that for each chain, you have to wait a long time for it to converge. So at the initial steps, they kind of come from an initial point, and it will like wait a long time to wait it until it gets equilibrium. And for that part, you kind of cannot parallelize it. And all in every chain is a Markov process, so every step will depend on the previous one. So if we wait until all the chains get converged, then you can just stack all the different chains together to get a larger sample, and that will make your uncertainties a bit narrower. But yeah, you have to wait until it gets converged. Yeah.
Thank you.
Yeah. Thanks.
So,
Q 他讲话，等一下接完最后。
yeah. So let's get connected. Welcome to join our Facebook like our Facebook fan page, and also we'll post our monthly talk events on our Facebook page. So there are 3 events in this month, so welcome to join them. The first one is building infrastructure with R. So it's a meetup event by Our Lady, and the second one is web scrapping with Python. It's hosted by a Python PyLady, and the third one is non-focus summit.
Yeah.
So
yeah. So has anyone heard of PyLadies or R Ladies? Any lady coder? Raise your hand. Lady coder. Cool. Anyway, so New York Times is partnering. I work for New York Times, and we're partnering with Our Ladies and PyLadies. So these 2 events on Meetup have already been full. But if you're interested, contact me. Just find me, and I'll add you into the guest list. And we have Sam here from Non-Focus, and you want to come up and just talk about the events you have coming up?
So hi everyone, I'm Sam. I'm from Non-Focus, this committee, and Non-Focus is effectively the organization that manages a lot of the open source data science projects, such as Jupyter, Pandas, what else? Yeah, there's like a whole list. Yeah, Jupyter Lab, exactly. And so effectively what we're doing is during PyData and NYC in September, we're hosting like effectively a kind of boot camp / hackathon to introduce people to open source data science. So if you use a lot of these libraries, and you're kind of curious as to how you could actually contribute to them in terms of like making a PR or a pull request in open source in GitHub, this effectively is going to teach you how to do that. And as kind of like a teaser, we're also including a kind of practical machine learning tutorial as well. So it's effectively just a way for us to get people that are normally not like techies into open source data science, and also just just to see what people are interested in. So if you're interested, feel free to contact me or Robin, and we'll send you more information.
thank you.
So our next event for TDP is here.
Yeah. So it is, the title is how much bias in your algorithms. So we have two speakers. The first one's Marian. She's a research scientist at Tabacrew. So it's like Tabacrew is a website, like kind of like scrap all the data and use it to hire data professionals. And the second one is Chalatai, and he's a data scientist. So please come join us next month. Yeah, it's August 31st.
Yeah, so this event has, the one in VR has been sold out, so if you want to get your ticket, this event is live. You can go to bit.ly/TDP 2018-0831. It's August 31.
Just
so it's
like our Facebook fan page, and you can know everything.
That's
Okay.
another one.
So we still have time for wrapping up. So you guys, if you guys want to stay for networking, the place will close at 9. So yeah, enjoy your time. Thank you.
Okay. Yeah.
For me, it was fine. I was thinking of the sneaky thing. Thanks for hosting. like people are starting to try things, and like things are like there are some things that are starting to work out. It depends on the task. Like right now,
You guys
I don't have it on my phone, but you guys have it. And then I'll accept your friend request. I haven't gone back in a while, but I need to. I definitely because they're great. They're great. Yeah, I'll add you on.